Okay, good afternoon everyone. We will be today talking about autoencoders, and specifically towards the end we will be talking about variational autoencoders. In the previous lecture we had discussed about variational inference. Can someone quickly summarize why we need variational inference? What are we trying to do?
We are fitting a normal we are fitting a normal with parameters mu or sigma or any other distribution with corresponding parameters as closest as possible to the posterior, minimizing the KL divergence.
Okay, excellent. So in Bayesian inference the task is to estimate the posterior, but we cannot do that because we don't have the evidence term or we cannot compute that tractably. So therefore we end up saying that let's use an approximate distribution, which we call the variational guide, surrogate, all of these are different names. And then we try to minimize the KL divergence between this proposal distribution and the posterior distribution. But to compute the scale divergence, we need to know the posterior, which was the first thing which we were trying to avoid. So what do? We compute the elbow, right? Evidence lower bound. There is a constant term which involves the log probability of data. We can omit that out and compute another term which we can then optimize over. We optimize over the parameters of the variational distribution, right? So we need that variational inference in the variational autoencoder, but before that we need to understand what an autoencoder is. As the name suggests, you're trying to use a neural network which has the same input and the output. You're auto encoding, right? And some of the reasons you do this is for dimensionality reduction. Could you think of any other reasons you may want to use an autoencoder? This is an autoencoder. We start with an input. We have an encoder G of phi. So this is a very nice blog post which is looking at the beginnings of autoencoders and towards the more recent trends also. So they're also showing that you're parameterizing the encoder and decoder differently. One of them is parameterized as phi, the other as theta. Typically these are neural networks. We start with an input, encode it to a bottleneck. What do you mean by a bottleneck? So neck of the bottle, right? So has anyone heard of this quotation? I think a thin neck at the bottle, something like that, prevents it from spilling over or completely being drained in very short time. So that is the small neck of the narrow neck of the bottle, which is constraining the representation. So all we're trying to do is, let's take an input 4 and try and boil it down to a lower dimensional representation, which can then be used to reconstruct the input via a decoder. And you want to do this in such a way that the input and the reconstruction are fairly similar to each other. And because you're looking at the same input and the output, what you say is the output, you're looking at the loss, which is the reconstruction loss. How well can you reconstruct the input given this encoder and the decoder? So they also so this is also a nice article in the sense that you also get a sense of the history. So you can see this paper from Jeff Hinton in 2006, which is talking about reducing the dimensionality of data with neural networks. It's not a very old paper that way, although this seems like a very trivial idea to start with an input and constrain it via a bottleneck, but it's very recent. But it also mentioned about some other work in 1980s, which can be found in the Wikipedia article. So they also mention, so let's think of this as this is an image. So if you were to do anything like find out the closest images, right? How would you do that? If I tell you find out the closest images to the digits in MNIST, images in MNIST, how would you do that? We would look at the latent representation and we would try to find out the distances, and there you could do KNN, right? So if you're looking at similarity searches, learning a good representation and then an algorithm as simple as KNN would often suffice, right? Similarly for songs. So I think I'd shown this earlier sometime also, how Spotify and other engines might work. You'll have songs which are basically time series data. You'll have to encode them into a vector representation, and then over that vector representation you can do a quick search. Right? So there's a lot of buzz going around on words like vector databases, etc. It is effectively boiling down to how can you represent different things as vectors. So how is this different from other dimensionality reduction techniques? And what other dimensionality reduction techniques do we know? PCA. So PCA, how is PCA different from this? Are you learning anything specific in PCA? You can almost think of it as a deterministic set of functions, right? But here you are learning an encoder and a decoder, which is heavily data dependent.
Sir, in CNNs also we have dimensionality reduction.
Is that a question? Is that an answer?
Answer.
I didn't fully get that. CNNs also dimensionality reduction.
In CNNs we have filter kernels that
Max pool.
yes, sir.
We have filters like max pool which can reduce an image to a lower representation. We can use strides, etc. So thus, if we are to learn this, the parameters of this encoder decoder model are this phi and theta. So what we'll feed in is a bunch of such images which have the same output, and we'll optimize the loss functions such as a mean squared error loss, which is between the input xi and the reconstruction. So you should very carefully look at the reconstruction. G of phi is the encoder. You go from x to z via the function g of phi. So z equal to g of phi, and then x dash equal to f theta of z. And if you were to just write it in one go, xi minus f theta g phi of xi, and you summing it up and taking the mean over all the n data points. Let's take this example and see some code. So I am defining a simple autoencoder. So typically whenever you see autoencoder like codes, you will see different sequential blocks, which just makes it easier to write. You could have also created separate nn.modules, modules, but this is a simpler definition or succinct write-up. We have an encoder which consists of a linear and an activation. I have specifically passed an activation so that I can use sign. I prefer to use sign activation in many cases. And then another linear. So input to hidden, hidden to z, where z is the representation size. And the decoder goes from z to hidden, hidden to input size, because the input size and the output size are the same. Finally, I have a sigmoid. Why do I have a sigmoid? Am I doing classification? You want the pixels to be between 0 and 1. We are assuming that we'll do that kind of manipulation. ReLU might have worked, but sigmoid is just safer. Forward is simple. In fact, this would be better if I write it as z equal to encoder of x and x equal to decoder of z. That way it's more correct. I am going to look at 1000 images from the MNIST dataset. I am ensuring that they're between 0 and 1. I create an autoencoder object, hidden size of 128, z equal to 32. And as usual, I always want to first verify the shapes. So my x is 1000, which is the batch dimension. This is the channel dimension 1, height, width. For the MLP, I don't really need the channel dimension. So I will just pass 1000, comma 1 into 28 into 28 as the input to my model. My model accepts the input size to hidden size. So I directly pass this to the model, and at least the shapes are correct, 1000, 784. And then I'm creating a function to plot the reconstruction. Fairly straightforward function. Some of these things will become clear when I show the latter part of the code. So this function didn't look like this initially, it was a simpler function. But because I wanted to look at various cases such as for variational autoencoder and VAE and MLP and CNN, etc., that is why this function looks a little bigger than it was. I always suggest to run the model in an untrained fashion first. So I run the model in an untrained fashion. When it's not been trained, I look at the max and the min values that I get after reconstruction. They're between 0.4 and 0.58. Doesn't look like a very good thing because we should ideally have the range, full range between 0 and 1. But the shape is correct, 1000, 1, 28. I can compute the loss on the untrained model. So this is R, which is giving me the reconstruction, and X, which is my input, and the MSE loss between them is 0.2318. Another useful thing you want to do is to plot the reconstruction for a batch of images. So you can also make use of various such nice utilities such as torch, which installs utils.makegrid. So these are the reconstructions that my model gives for 20 such images. They're fairly random, you don't see any pattern, and that this is as expected. I am calling the training function, which will run for 1000 epochs or a batch size of 500, mean squared error as the loss function, and then Adam is the optimizer. The loss is mean squared error, which is essentially the reconstruction error loss that we're looking at. Now, if we look at the min and max of the reconstruction for the 1000 images, it's 0 and 1, which looks good. If we look at the losses, they have seemed to have almost converged. Probably for a few more iterations I could have gone further. Let's look at the reconstructions. Do the reconstructions look very sharp to you? Right, so we've been able to do a very good job at reconstruction here. Should we stop here or should we do something else? The next topic I have written is convolutional autoencoder, but why might we need to do that? Why not? Because we are getting excellent reconstructions here. MNIST is too simple, but for this data set, should I just use MLP always for autoencoder? I can't say that until unless I've seen the performance on an unseen data. So there I can see the reconstructions and how good or bad they are. So I'm looking at model X and 20. Let's see if I can create some test index, another 1000. And what do we see? Is there a bug? Do I need to rerun some cells or is this as expected? Let's verify again. Let's run for over the trained data set. Oh, okay. So maybe I need to rerun. Oh, because when I ran this cell, this model object got instantiated, which is why this is a poor piece of code where these two things are coupled. Okay, you can see it's fairly good, but you can also see that it's not as good as it is on the trained data set. Right? The next thing you may want to do is to look at the latent dimension and vary it and then see the reconstruction accuracies, both train and test, and then probably you will find an optimum point. You should ideally do this over a validation data set, not look over the test set. But because we know that convolutional autoencoders are likely to be better for image, convolutional neural networks are likely to be better for image like data, so we'll use them. Our encoder is now again a sequential consisting of conv layer activation, conv activation, conv activation, flatten and linear. So I very carefully designed these so as to ensure that the number of parameters doesn't blow up. And then finally I go from 784 to the latent dimension, which is again something I'm passing. So I'm specifically creating this design because I want to vary the instance of this model according to the latent dimension and see the reconstruction accuracies and quality. I am not using a pool, but you could have also used pool, conv pool, we could have used it like that. The decoder would be almost the opposite of this. So instead of flatten, I have the unflatten. Instead of linear 784 to latent dimension, I have a linear from latent to 784. Instead of conv, I have con 2D. But you'll have to be a little careful about the dimensions, etc., to ensure that you get the correct shape. Finally, I have the sigmoid. I have x equal to z equal to self dot encoder and x equal to self dot. If you want to make it even closer to the article that we have, this is the way we may want to write. I also typically like to do a dot summary to get a sense of the number of parameters that I have. I typically vary the model to ensure that I can get very quick runs, especially in a classroom like setting. I don't want to be waiting for 5 minutes to compute some results. So I typically look at these output shapes and the number of parameters and tweak them. Again, you may want to run your model through some simple input and see the shape. I will now be creating this conv autoencoders with various latent dimensions, going from as simple as 2, where the visualization would be very easy because in a 2-dimensional space you can directly, without using any dimensionality reduction technique, you can directly use and see what features we are learning. And I'm going till 128. I'm creating this con AES objects dictionary where I'm just instantiating for each latent dimension. And I'm also doing this so that you can see the various sizes according to the latent dimension. This one seems to have 0.26 MB forward size and the total size in MB is 0.29, whereas for the model with 128 hidden dimension representation, it's about 1.05 MB. You can also view this as scrollable element and see all the details. Like the total number of parameters is 204,000 and here the total number of parameters is 6,000, 7,000. So it's quite different, the number of parameters that we have. And for each such latent dimension, I will train the model. This is showing the reconstruction losses that I get for different latent dimensions. Can someone quickly tell us why we see such a trend?
More latent dimensions are able to capture more features.
The more the latent dimensions, more you have the capability to look at the specifics of each and every image so that you are able to fine tune, tweak the reconstruction for each of them. But if you have very low number of latent dimensions, you are trying to squeeze all the ones, all the zeros, all the twos, all of them to just a 2-bit, two length vector, which might not be very convenient to do. Which might not be very good design to do in terms of reconstruction. Now we can look at the reconstructions. This is with with the latent dimension of 2. This seems to be worse than MLP, right? And while we are at it, we can now keep plotting the reconstructions for the X test also. And here it seems okay. I would say comparable, probably comparable or slightly worse than the MLP, But if we now plot the reconstruction for 4 over the train, or 8 over the train, or 16 or 128 over the train set, the 120 over the train set looks fairly sharp. Let's see how this does over the test set. Fairly good, right? So now we can have some more confidence into that, saying that this convolutional autoencoder with this dimensionality is probably doing a better job at reconstruction compared to the simple MLP one. Now, one of the reasons why we are talking about autoencoders is for generative models. Right? So there has been a huge deluge of generative models. Like typically people are using things like DALL-E and other things, MGen. These are probably one of the simplest methods which can use to generate new samples, new images. How? How can we generate new images? Okay. Suraj, how can we generate new images using the autoencoder architecture that we have? Let's look at this diagram, right? So we go from an input image to an encoding to some representation. In this case, this is if we use a latent dimension of 2, this is a 2-dimensional number, right? And we take the 2-dimensional number, dimensional vector, we pass through a decoder and we get an image. If we vary the 2-dimensional vector, will we get a different output each time? So what is your answer now? How can we generate a new image given the autoencoder? We are generating new images because you can vary the input by passing in a different input. You can create any new image, right? Probably unseen images. You've not seen those as a part of your training process. We will do that right now. We'll want to pass, so we'll do a Z. A Z is a latent representation, which is a random number, so a random normal with the dimensionality of n numbers, n figures we want to generate, n images, and latent dimension is the shape, and we pass it through the decoder. That's all we have to do. Create a random vector of n images of shape, latent dimension, and pass it through the decoder. At the end of the encoder, let's see if we have anything or not. At the end of the decoder, we definitely have the sigmoid. I don't think so. We don't have. So is the question that if we had an activation, let's say ReLU, we would then, if we give any random input, it is incorrect because the random input can be a bit negative also. We don't have an activation. And it's also typically a good design, simple design to leave things in linears like we have done. You leave the output as a logits in the unconstrained space. We then, okay, what do you think will happen if I call this method? Plot random outputs with 20 images. It will randomly generate a vector of 20 cross 2, right? So corresponding to each 2-dimensional vector, I'll create an image. Do you think this will work well or no? You should not have seen the answer. Okay, why? Oh, it looks okayish, right? Not that bad. You can see some buns in here and some nice drawings. Yeah, we yet don't know the encoding space in which the latent space in which the entire data set lies. But anyway, let's still see the random outputs for different kinds of latent dimensions. With 8 we get this. Totally gibberish, right? Yet the reconstruction was better for 8. So does this look counterintuitive? Let's look at 128. So if we keep going in this way, I think we may end up generating QR codes also, right? It's not getting better anyway. Okay. Okay, excellent. Before that, I also want to show you another thing, interpolation between 2 points in the latent space. I'll pick up 2 points, z1, z2, and I'll linearly interpolate between them in steps of n. So my z of I is z1 plus z2 minus z1 into I in over n minus 1. Right? So I am starting from z1, I am going through z2, that vector, in linear steps, and then plot those interpolations. So I'm starting with 5, or I think it looks like 5, and I'm going to 0, and this is with the encoding dimension as 2. Looks okayish, doesn't look very good. Now let's look at a better visualization in which I have a slider, so I can change the input. I'm varying the inputs. I can vary the other one also so that it's not always 0. It looks a little hazy only. That's also one of the main reasons the latent dimension is too low. If I increase the latent dimension, you can see the images getting sharper. At this stage it's very sharp, and so you see that we're going from 4 to 7 through 9, almost something like 9. If we pick up, is there a question?
Yes, so this means that they are 4, 7, 9 are closer to the latent.
It means the 4, 7, 9 are close in the latent space for this particular model. If we view for latent dimension 4, it's not very clear, not very sharp. 16, what do you observe from this? From just this qualitative view, did the 8th latent dimension look better than, let's say, 128? Right, in terms of continuity of the latent space, looking at different digits, because this one has produced a lot of non-number like images in between. And then we finally come to the scatter plot, where we look at these images on a 2D space. We can see that zeros are spread over here. We can see some collection of 2s over here. What do you observe from this plot about the proximity of certain kinds of digits?
This is for latent dimension 2.
Yes. If this is not for latent dimension 2, we will be plotting only the first and the second dimension, unless we do TSNE or UMAP or any other dimensional reduction. Okay. What can you say about, this is 7, right? What can you say about 7? 7 is close to 9, which makes sense, which is close to 4, 4 and 1, right? 0 seems to be quite different, but there seems to be 1, 9, which is close to 0. Now try and understand the process of drawing a random number via the normal distribution. Where is that likely to lie if I draw from 0, 1 normal? So mean 0, variance scale 1. So it's close to 0 only, right? We can actually plot that also. So some z's equal to torch dot random normal 1000 comma 2 and plt dot scatter. Let's see if we are able to view them or not. Let's not. Right. So can you see that the randomly generated numbers lie here? Do you have anything in the representation over here, in the latent space over here? No. Does it explain why we may be getting, when we are randomly generating, passing this randomly generated input to the generative model or to the decoder, we're not getting something very useful, right? If we had instead passed in this range, we may have got something better. Another thing we can see is system representation, but let me come back to that later. I'll first show the plot and then we'll go and understand what we're trying to do. Okay, what are we doing here? Okay, what do you think is happening here in this plot?
We have just input all the x comma y's from that graph.
We have given a range of x min, x max, y min, y max from the embedding that we had learnt. So let's say y min is minus 12, y max is 0.5 and x min is minus 8, x max is 6. So we've drawn some n numbers in each dimension in this, and then we have seen the latent we've seen the regeneration that we can get from each of those latent vectors. First, towards some corners we don't see anything, and that is explained from the latent dimension also. Like for example, while we are going y min is minus 12, but corresponding to x min, this region we don't have any digits. So let's see where the x is also minimum and y is also minimum. X minimum and y minimum, we see some gibberish. Right. And similarly for the other corners also, we can see. Right. X in the middle, y in the middle, we can see a lot of very good reconstructions, which we see here. And we are also able to see the interpolations. Right, we can see some level of smoothness between these. Okay. What do you think will happen if I either keep increasing the dimensionality of the latent space, or if I keep training for a long time? What might happen to this scatter plot and the reconstruction accuracy? Do you expect the reconstruction accuracy to improve or get worse? It should always keep improving. Eventually you may overfit. What might be the notion of overfitting in this plot? Sorry? There will be huge variance, overfitting, large variance. What might happen is that each image in your data set might be very far from each of the other images. So you have some confusion in this current scheme, right? That is because this particular 9 looks like this 7, etc. But if you were to expand all of this space, moving very far from each of the other points, you'll almost have a perfect reconstruction. But what do you lose? Generalization. You lose the whole meaning behind the latent space representation. You were trying to encode similar images will have a similar latent representation, but that is going to get worse. Right. what is the solution to that? How can you impose some kind of regularization? We have a validation scheme, but let's assume we don't want to be using a validation, but we want to propose some regularization. Whose strength you can control over the validation? So I'm not talking about, so let's assume that for a fixed latent dimension and fixed number of epochs, if you have to train, what other kind of regularization can you apply? Sorry? Dropout we could, but let's use something more fundamental, which is talking about the problem, which is addressing the problem which I said. We don't want the representations to get very far from each other. We want similar images to be clustered together, to be encoded in a similar space. Okay. Anyone else? Sorry?
Add some noise to the representation. Try to learn.
Okay. So we've had two good answers. Any other answer?
So you can add a background at the end of the encoder that will force the latents to be zero.
Okay.
We can penalize based upon the distances of one region.
Okay. So all of you have said fairly good answers. All of them are valid answers and different variants. The one which we'll see is that we'll say that we want our embeddings to be very close to 0, 1 normal distribution. There is a probabilistic view of why suddenly you are bringing in a normal 0, 1. The other way you can think is you are trying to learn something which is shared across different images, and one way of enforcing that is by putting a 0, 1 prior. It will come to that in a second, but before that, let's look at certain metrics which we wanted to calculate. Like, let's say the distance between representation of two images, and I'm also finding all the occurrence of a specific digit. So I'm finding all the zeros, all the ones, their indices. I'm looking at the distance between the first 0 and the second 0. Right? I have different zeros in my data set. That turns out to be 0.248, and I'm looking at as I increase the dimensionality, what do you expect of latent? Distance should increase. Right? Can you see this? As we increase the latent dimension, the distance between pairs of images, in this case they are the exact same images of the same digit, that is increasing, which is telling you more about the discriminator power, telling you about how well they make it refined to be reconstructed. But it is also giving you hint of that if we keep doing this further, or if we don't have any kind of regularization, this distance may go till infinity, and we'll get perfect reconstruction on the given data set, but poor generalization. Okay. Before we come to variational autoencoders, we'll revise this vanilla autoencoder that we have seen. We went from input encoder G5 to bottleneck Z, there to a decoder via F theta decoder to X prime. We said that let's learn G5 and F theta networks such that X prime is as close as possible to X theta. There is another autoencoder known as a denoising autoencoder, where the idea is fairly simple. You start with an input image, you can do a bit of masking on that input image. So you are partially destroying input. Where have we seen partially destroying input earlier? Dropout, right? This is similar to dropout. You mask certain entries, you make them zeros, etc. There you're doing on the activation. Here you're doing on the 0th layer activation, which is the input itself. There are other variants to it. You can add noise, etc., right? And then you get a corrupted image. You pass it through an encoder, bottleneck decoder, and you give the correct. You look at the reconstructed input. You match with what? X tilde or X? X, the actual image, not the masked image. You're trying to then reconstruct. You're hoping that by this process you'll be able to learn something more than just what if you just gave the original images, this may also provide some notion of regularization. And this article, they very nicely add that this was published in 2008. And they mention that this was 4 years before the dropout paper, which came out in 2012. So the idea existed to some extent, but was not leveraged that way. So that is why I've said that this is a very nice article. It gives you certain historical perspectives also. The next kind of autoencoder is a sparse autoencoder. What do you think this might be doing? Sparsity in the latent space, what do you think?
I think it increases the input size.
Increases input size. Anyone else? What do you typically understand by sparsity? Lots of zeros. So what they say is that they put a sparsity constraint on hidden unit activation to avoid overfitting. So what you are probably trying to say is that there is some set of nodes, there are some set of features which will get activated for certain digits, and there are certain other features which will get activated for some other digits, right? So if each of the feature gets activated in different weights for each of the digit, right, it's likely overfitting. Right? You want to say that there are some features which will get activated, which act as a basis and for some digits, and there are some other features which act as a basis for some other digit, some other number, and they'll get activated differently. How do you think this might get implemented? This is an interesting exercise. Interestingly, this might also involve K divergence. You'll typically be given a sparsity ratio which you want. You'll maybe want only 5% of the nodes to fire. And an activation or firing node, you can define it as if its activation is above a certain threshold. So the central goal is always to come up with a loss function. You'll always have a loss function which has to have a reconstruction element, plus you'll have to add some loss for the sparsity constraints. Wherever the sparsity constraint differs from the target sparsity, you'll have to put some loss. The target sparsity I've given to you, which is some row value, and you'll have to compute your own sparsity value also, that you can do. What do you do after that? You could do L1. Or you could compute so this is your rho j hat for the lth layer. It's looking at the number of units which have been activated divided by the total number of units. You want it to be as close as possible to rho, and then you can mention that this is rho is the probability of heads, probability of success of Bernoulli distribution, and you're minimizing the K divergence between rho and rho hat j. You could do it this way, you could do L1 norm, etc. All of them are valid ways to do. So we'll see this pattern very often in machine learning, probabilistic machine learning also. You'll always try to preserve the main loss, plus you'll add some loss which adds certain constraints, which adds some geometric interpretation or adds some physical meaning to your problem. In this case, we are adding the sparsity constraint. In the previous case, we modified the input and denoising autoencoder. So we said that let's also target a certain sparsity value, right? So it's not very difficult, but it's very nicely put together in this article. There are different variants. I will not go into all of them. You can read into all these. Is there a question? So next we come on to variational autoencoder. What do you think variational autoencoder will do? It has to have some element of variational inference, otherwise it will not have been called variational autoencoder. So variational, what are we trying to do in variational inference? We are trying to minimize the KL divergence between what and what? Between a proposal and a posterior. We can approach variational autoencoders in that perspective also. Or let's not forget the most recent thing which we discussed, which is the loss plus some penalty perspective on autoencoders, right? So we just discussed that our latent space is getting very far from each other. Right? So we said that let's put some penalty on it, and that penalty could be that we want our latent space to be very close, as close as possible to the 0, 1 normal distribution. Now what do you think we'll have to do? We'll have to have two losses again. The first loss is the reconstruction loss. What is the second loss? Between
Standard normal and that distribution of the latent.
So we are minimizing, we are trying to minimize the scale divergence between the standard normal and the latent distribution space. But the latent distribution space is currently a vector. It's not a distribution. So the latent distribution, the latent distribution, the latent dimension that we see in currently right, that's Z. It is currently a vector. If you have to convert a vector to a probability distribution, what do you need to do? We have to parameterize it via any distributions parameters. So what we say is, instead of learning Z, which is self.encoder, which is a vector, I learn the mean and standard deviation of the latent dimension. So I learn a distribution that way. If I do that, I will write the code as follows. Everything else till this point remains the same. Instead of learning at latent dimension number of parameters, I learn 2 parameters per dimension because I want to learn a mu and a sigma, or a log sigma, log variance. Similarly, I'll start from latent dimension and we'll go to 784. Is this a bug? Here I'm going, so my encoder is ending at 784 to latent dimension into 2. So my encoder finally has 2 into latent dimension number of parameters, but my decoder is starting from latent dimension. We don't take the mean. We take a sample. But good, some of you are noticing that it's not a bug, and the forward method will get a little varied. X is passed to the encoder and we get a new value. We chunk it up into mu and log variance with dimensionality over the first axis. I get the standard deviation, I get the epsilon. So this is the reparameterization trick. I could have just done the R sample method also, but this is effectively, I am generating one sample from the normal distribution, standard normal. I am adding mu and multiplying with STD, and this becomes my Z vector that I have learned, Z sample that I have obtained, right? After this stage, my decoder still has the same input, Z, right? So this is where the main difference is coming in. I am not just learning I'm just not learning the point estimate for the latent space. I am learning the mu and the sigma, which means I'm learning a distribution for each latent dimension. And then in the forward method, my decoder still accepts a single latent vector only, right? So in order to pass in a single vector, I have to somehow create a sample out of it. For the sample, I'm creating the reparameterized sample. Why am I doing the reparameterized sample? Why not just a regular sample? So that we can backpropagate. Or we could have just used R sample here. And I'm returning X, mu and log variance. Previously, I was just returning the Z, or just X prime, right? Here I'm returning the mu and the log variance. Why? In addition. We have a KL loss element, KL dimension. So then we create a VAE loss. So this is actually a variant of VAE. It's called beta VAE, beta variational autoencoder. So the beta term comes in, we have two loss components, the reconstruction loss plus beta times the KL dimension, the KL divergence loss. I compute the reconstruction loss as before. I take between x hat and x, the reconstruction error. I get the standard deviation by exponentiating the variance, right, log variance, and divide by 2. And then I have my prior distribution, which is normal 0, 1, and my posterior, which is normal with mu and standard deviation. I compute the KL divergence between them. Right. And then I'm from a, so if you view just from the regularization perspective, for the denoising and autoencoder, or for, not for the denoising, for the sparse autoencoder, we had the loss term, reconstruction loss, plus beta times the sparsity loss. In variational autoencoder, we have the reconstruction loss plus beta times the KL divergence loss, or the regularization term that we have added, which is trying to enforce that the latent space is close to 0, 1.
Why are we adding the two loss? Can we not have separate losses for both the KL divergence and the other loss, MSA loss?
So overall, we have a single network. We have two sets of parameters, theta and phi. Both of them go into the encoder decoder, and eventually we get the reconstructed images. Right? So we will want a single loss which does both the reconstruction as well as takes care of the regularization. Now remember how we were doing linear regression. We had y minus, we had a mean squared error between y and y hat, right, term, plus lambda times some L2 penalty on the theta. Right? We had a single loss where we were adding two losses. So similarly, we are adding two losses over here. Everything else remains the same. I will create a conv VAE mnest object. I am, let's see if this is saved or not. No. So let this run for a few seconds. While it is running, so in Kevin Murphy's book, in the chapter on variational autoencoders, they mention about why this might be better than just a regular autoencoder. They mention that they're very similar to deterministic autoencoder, and they mention one of the differences, the encoding is deterministic, whereas here the encoding is non-deterministic. And they're looking at the Celebes dataset, which we've been using for some time, and they're showing the unconditional image generation using VAEs trained on Celebes with the deterministic autoencoder, which is the vanilla autoencoder that we have been looking at. And this is on beta VAE, which is the same which I'm just showing you, where the beta term is 0.5, beta equal to 1, etc. Right? Which of them looks better? The bottom one, right? So this requires a very careful design into these beta parameters, as well as there are a lot of things which we'll see in the next few minutes. This is not very easy to generate, and this is unconditional image generation could mean that you're feeding in random vectors. And this is likely to happen because the random vectors are likely to be, because of the KL divergence penalty term that we put, these for the beta V's, the latent space would be closer to 0, 1, right? Whereas normal 0, 1, whereas this one could be in any space. Therefore, if you give a random input, vanilla autoencoder might not work well. Question till the time the code is running: is beta equal to 0 the same as the regular autoencoder? Let me ask this question in the exam also. Is there any difference, or are they the same? Who say they are the same? Okay, anyone who says the different, why? Model architecture is different, slightly different. And sorry? There is a sampling term which didn't exist there. So sample can introduce some amount of stochasticness there also. So there are those few things you need to be aware of. And in the VE loss, we're looking at the KL loss. What we are assuming here is that if you noticed here in the forward method, we are generating a single sample, right? So if you notice, what we are doing is we are doing Monte Carlo sampling, but with just one sample. Right? Typically not a very good design. You can always increase the number of samples here, right? Compute the KL divergence with the expectation over multiple samples. That might turn out to be slightly better than just over one sample. So that will be probably one of the reasons why the reconstructions that we will be getting using this conv VE are not as good as what we are getting with the regular autoencoder. So in this training procedure, I am running this big loop, 2 loops. I am looking at this latent dimensional subspace of 2, 16 to 56, and I am looking at betas equal to 0 0.0, 0 0.001, 0 0.01, 0.1, 0.51. There is some literature which says that which takes the beta much greater than 1 also. Right? But beta is up to you now to what to take. I think in their article also they mention beta VE. Beta greater than 1 applies a stronger constraint on the latent bottleneck, limits the representational capacity of Z. And for some conditionally independent generative factors, keeping them disentangled is the most efficient representation. I don't know what that line meant, so let's skip that. We'll have to read that in more detail and understand the context. But anyway, the training is done. Now let's look at the reconstructions. Okay, this is latent dimension 2 beta equal to 0.0. We notice this is probably slightly worse compared to the regular autoencoder that we had, right? One of the reasons could be you're also trying to learn more number of parameters through a similar data set, right? Second, you just have one Monte Carlo sample. What do you think will happen when I move to beta equal to 0.01? Will the reconstruction get better or worse? The reconstruction should always get worse because you are trying to now also get in an additional term, which is the KL divergence term. Right? Look at what happens at beta equal to 0.5 and beta equal to 1. Right? It's almost a very hazy representation. So at high value of beta, it's saying that let's now try and optimize the KL divergence. If you were to look at the space, it may be all close to zeros. So it's not even looking at the reconstruction. All it's saying is that the KL divergence term factor is very large. So we have to sum optimize for that. So let's put all of our energy in that and let's optimize the parameters of the network in that way. With beta with dimensionality equal to 16, you can see it's much sharper images. And even with some amount of beta, it's still reasonably good. Right? And similarly with beta with latent dimension 256, even for a moderate value of beta, we can get quite good representations.
Does that mean for larger beta we need to train the model more?
For larger beta, we may need to not just train longer. So we can see the plots there. Many of them, if you notice, they've actually converged. In fact, for the larger beta, they've converged quite early. And the beta is that large that it ends up completely dominating. Like you may have to do some readjustments on the scales of both these quantities in order to ensure that they are summing up nicely. Both the terms are playing a part. And for this particular example that I've taken, it seems that beta equal to 0.5 is a very large term. So it's something which is specific to the data that you have also given, the data dimension that you have.
How do we validate if a particular beta would be better? Because reconstruction now slowly goes by, right? So visually, is it possible to?
So visually we'll see certain things. The image generation was likely to get better, and of course there are some metrics you can, like visual metrics you can use. I'm not sure, but maybe even on the quantitative metrics on the validation set you can show that it's getting better. Right? But for unconditioned inputs, it does seem to be doing better. We saw that just a few minutes back. So we can see that as we increase the latent dimension, what happens? Right? The reconstruction will get better. And let's now plot the scatter plot for latent dimension 2 and 0.0 as our beta. Just look at the scale. We can see that it's going from minus 7 to 8 and about minus 1 to 11. Right. What will happen if I increase beta? They'll move towards the origin. Right. So now just look at the scale. It's going from minus 3 to 2 and minus 2 to 3. Right. The whole span has reduced, but consequently you'll also see that some of the points may start getting infused. For a much larger value, 0.01, we can see now the space is even further reduced, right, closer to 0.1. And this model itself had a very limited capacity, only 2 hidden representation, 2 latent dimensions. Therefore, also it's not a very good fit. For larger, it would be better fit, but we can't visualize them in 2 dimensions. So now we can also visualize the latent space for latent dimension 2 and 0.0 as beta, and we can still see a lot of these corner spaces having nothing reasonably good. Now if I increase the beta to 0.01 and still on the corner spaces I see something useless looking. So then what is the point of VAE? Is there a bug?
But I think we introduced beta to prevent overfitting.
We increase beta to reduce overfitting, yeah.
So that's why we are getting weird reconstructions.
We're getting weird reconstructions, but still the reconstruction visually is not looking that good. So, of course, overall there will be very slight reduction in reconstruction performance because we have now 2 competing terms. What might have gotten better between this scatter plot and this scatter plot? So what is hidden from you is the ranges of the plot, x min, x max, y min, y max, right? And they are quite different in both of them. So these numbers are closer to 0, 1. Right? Now if you give a 0, 1, 0, 1 normal, you're likely to get much better reconstruction, which is the objective which we started with. If you give an unconditional input, how good reconstructions can we get? Now let's compute a few numbers to see if they're making sense. We now look at the distance between the representation with latent dimension 2 and 0.0 beta, and I'm looking at the first and the second 0. So they're both 0, same digit. If I look at the same problem but with 0.01 beta, the 2 zeros are naturally closer now. Right? That makes sense. To the 2 zeros, the 2 representations corresponding to zeros will become closer. Let's also see what happens if I increase the beta quite significantly to 1. And now these 2 zeros are very, very close. So thus far this particular trend looks good, but there will be an opposite trend also. 2 images of different digit may also start getting closer. So that is also something we should look at. Let's look at the first 0 and the first 1. And with beta equal to 0.0, the distance between them is 10.0. and with beta equal to 0.001, between the first 0 and the first 1, the distance is 3.9 or 4, right? So now if you want to understand this better, this is left as a to-do exercise. You have to look at the ratios between objects between two inputs which are of the same digit and two inputs which are the different digits. And I really want to average this over all the pairs. We did a similar exercise in the cursive dimensionality lecture in the ML course. There are quite a few to-dos which I am leaving in the interest of time, and I think it will be good for you to explore. What will happen if I, instead of, now if a model is trained on MNIST, but I give a fashion MNIST as an input, what might happen? I'm limited to showing scatter plots only in 2 dimension because I'm not using TSNE or any other dimensionality reduction. You can use that. We can create animations for interpolation rather than just dragging. We can work on harder data sets, CIFAR, Celebi. We can show for varying number of Monte Carlo samples. We can show the performance of the model on test data. We have seen it to some end, and show from a Bayesian perspective. The Bayesian perspective of this, I would leave that as an exercise to you, which is a very interesting view, which will help you understand why the KL divergence suddenly came into play, right? So I just start this, but I will not end this particular section. It's for you to self-study. Let's consider this generative model. It starts from latent dimension z, right? We can, which was distributed as per some prior distribution, right? Z is distributed as per some p of z, which is typically normal 0, 1. From this z, we can draw a sample data, we can draw a data point xi, which is distributed as p of x given z, right? Thus far this makes sense. We can apply the Bayes rule, p of z given x equal to p of x given z, p of z divided by p of x. P of x is not computable, which means we can try and approximate p of z given x via a variational distribution. And we want to minimize the KL divergence between q lambda z of x and p of z given x, which will come out to be some expectations of certain quantities, which will come out to be exactly the same as what we have seen, right? So here the KL divergence comes in very naturally in this, not as a penalty term, but from the first principles of Bayesian understanding, we are able to bring it. I leave this, and in this article also it's explained. You start from a prior z, which is normal 0, 1. You can then obtain a sample x through that, and you can apply the Bayes to get the posterior distribution p of z given x, but that we can't compute. So therefore we propose a variational approximation and then through that we can get the same answer. I wanted to now, for the last few minutes, just quickly summarize the entire course, what we have done. In the beginning, we started off with the introduction logistics, where we looked at the problem of uncertainty in machine learning, and we looked at various applications such as a Tesla car or medical imaging, etc., where uncertainty is quite important. We looked at the dog human being example. The model quite confidently says this human being is a dog. We said that let's look at the Bayes rule for ML, where we introduce the terms such as prior, posterior likelihood, and for the next few lectures we just focus on that. Towards the end, we said that Bayes is not everything in probabilistic ML. There are other ways to get in. We looked at some very nice examples such as heteroscedastic likelihood, for example, or we looked at a neural process. We looked at various variations. When we looked at the Bayes rule, we initially looked at distributions, sampling, as well as the likelihood term. We looked at the optimization process of MLE. Then we looked at the map, and then we looked at the full Bayesian. We looked at the biased and unbiased estimators. When we are doing MLE, are some of the estimators biased, unbiased? And We finally took a non-trivial example of Bayesian linear regression where we could compute the posterior in closed form. But we said that in many cases, even if we can compute the posterior in closed form, we often need to predict on new samples. So we need posterior predictive. Many cases we have to use something like Monte Carlo sampling. So we've looked at a bit of sampling and we looked at Monte Carlo sampling. We then looked at, for logistic regression, we looked at a very specific application of Laplace approximation where we propose a specific distribution as the approximate distribution for the posterior. We looked at various properties of Monte Carlo sampling. After that, we looked at how to get uncertainty out of neural networks using very simple mechanisms such as heteroscedastic likelihood. We looked at two types of uncertainty, aleatoric and epistemic. We then looked at various kinds of sampling methods. While we looked at Monte Carlo sampling, we wanted to look at, gradually go into more efficient sampling techniques. So we went into importance sampling and then some MCMC techniques, which we have said that that's the gold standard for Bayesian inference. Whenever possible, we should be, like if we have infinite compute, we should use MCMC. We looked at some theory of MCMC, including some theory on Markov chains, stationarity, and certain properties. We came back to calibration to see what it means by the dog cat example, what it means that it is there's 90% chance of rain. What does that mean? We looked at MC dropout and deep ensemble, which are fairly common methods of obtaining uncertainty in neural networks. And then we went into meta learning concepts. What can we do if we have a new task at hand? We looked at variants, the simple more Bayesian inspired variants such as hierarchical models, Bayesian hierarchical models, and then the more neural network like models such as hypernets, which we learn in new network to predict the weight of another network, and a neural process which is encoder decoder architecture. We looked at more specifically for science coordinate network hypernets, and then we also looked at another variant of this problem. So we've been dealing with this problem of not having enough data points in supervised learning settings. So one such method to solve that is self-supervised learning, where we have a large pool of unlabeled data, and we say that can we do some self-supervision on them to improve our estimates. And if we cannot, or in conjunction to that, we can do active learning, where we say that let's strategically query a set of points to label. We looked at a very similar problem of Bayesian optimization. Active learning, the goal is to reconstruct the function as good as possible. Bayesian optimization, the goal is to maximize that black box function. We typically use that in hyperparameter tuning and other kinds of setups. We then looked at variational inference, but that required us to first understand the distance or the divergence between two distributions such as via K divergence. We understood the basics of variational inference, which is to propose a variational target surrogate distribution and then match it as close as possible to K divergence. We looked at few variants of it. One, if you want to find out K divergence between two distributions of different families, we end up using Monte Carlo sampling to compute their expectation in the K divergence formula. Second, we looked at reparameterization trick, which makes the whole network back propagatable. We looked at two specific examples. We looked at a specific example of coin toss linear regression. And then we said that if you want to use it in a practical problem like setup, we'll have to look at the elbow evidence lower bound term instead of optimizing the K divergence, because we don't know the log evidence term. And today we looked at variational autoencoder. We started with a regular autoencoder, and then we are finishing off with how to add variational aspects to it to make the whole latent dimension more regularized. There are two variants, there are two views to this. One is just the loss plus regularization term. The second is from a Bayesian perspective, we can derive the same thing. And I'm leaving you with two very nice articles which do this. There are some small tidbits which I still need to do, including a little bit more on the AutoGrad like functionality for reparameterization. There are some new things, there are some more doubts which I need to clear on that. There may be one or two small things which I may still send you. For example, for neural process, or I can just say that right away. So neural process, we didn't yet look at the notion of uncertainty, but the way the uncertainty in neural process is introduced is very similar to the way we done in variational autoencoder. So if we look at neural process, family. So here also we have an encoder and then we have a decoder. You can again make the encoding uh, as a distribution, similar to the way we have done today, right? You can, instead of just learning a vector, you can learn a mu and a sigma, and then you can compute z, and that's how you can trick it, right? So that's all I had. Any questions? So that's all I had.